There's a really good website at Rice University. There's the EE department there has a group that has done an extensive research in biology and zoology in the use of frequency time analyses. And I pulled off these three images, which are exactly the spectrograms that I was discussing earlier. Basically, these are bat chirps. And these are ultrasonic chirps on bats. When they range, they don't produce a simple blip. They produce overtones at different frequencies that change with time in a certain way, and they use this to do their ranging. And
what's the axes on these things?
Frequency and time, just like the other one. And the color is intensity of the spectrum. One good reference that I've used and from which I extracted the table that I showed you earlier is from 13 years ago by Leonard Cohen. It's an IEEE proceedings that has a rather extensive review on the whole use of frequency time techniques. I'm sure there are other more recent updates to such a review, but this has been a good article that I've used in the past. And it was applied by Warren Anderson and Balasubramanian to gravitational wave data in a PRD article that appeared a few years ago, looking specifically how one might use these techniques for LIGO data. Thank you, Kip. I spent some time in preparation for this lecture and created a serendipitous chart in which every astrophysical type of source you could imagine happened to be in coincidence on one stretch of time. If you squint here, I think you can see this trajectory. That's what a chirp looks like in such a representation. These are events that have very short duration in time and contain consequently a larger portion of frequency domain. So these would be glitches or bursts of whatever type you might imagine. This is a very narrow spike, and this is a broader one. And I don't know if you can see it in here, but there's actually a representative simple signal of what a pulsar might look like in here in the middle of the band. You see that line going across? So your eye is actually a rather well-connected neural network that's able to do image processing. And unfortunately, we're going to be restricted to doing this in the blind in the computer's guts using digital signal processing rather than image signal processing. So what you might see on here is this portion of the chirp. You'd never even, your eye certainly would not detect that there's a chirp in that signal. It looks just like regular old white noise. And that's because your eye is really good at detecting this pattern. If you were only given this representation here, you would not be able to make such a definitive statement that there was something of interest there. Bursts, on the other hand, or at least at the signal to noise that I injected them, are rather straightforward. And this is what the putative pulsar signal would look like. Once again, it's mud in the noise that you really could not pull out if you were simply doing a frequency analysis without concentrating the power of the signature into a frequency bin, such as is done by the frequency time map. And if you had a very high signal-to-noise pulsar, you would be able to see that even though there's a signal in here that depends sinusoidally on time, over sufficient epochs corresponding to fractions of a year, if you could observe it for so long, the frequency would be modulated due to the Earth's motion around the very center of the solar system. And the magnitude of that effect is approximately a few parts in 10 to the fourth frequency shift. And if you could then further observe on a scale of a day, hours, you would then see the fact that LIGO detectors are orbiting, are rotating the surface of a spinning Earth, and so there's another variation that's much smaller, a few parts in 10 to the sixth, correspond to the daily rotation of the Earth on its axis. But the point is that you know this has to be there, and so you can come up with clever metrics by which the degree to which this evidence for such signatures appear in the data can be used to make further improvements in confidence statements about whether this is really an astrophysical signature as opposed to a line spike of some sort. If you take these data and then produce an FFT over the entire time series. Let me see if I can go back. So if I do an FFT of this, and then later I'll consider the FFT of each of the separate pieces individually, The background, just the gray mottled pattern corresponds to I just injected white noise, and this is in a log-log plot, the white noise spectrum. The CW signal I injected at 100 units of frequency, and it's a clear delta function with no background if you looked at that signal by itself. I had an exponential ring down at the end at very high frequency with some bandwidth because it had a finite duration and time. The bursts occurred with two different windows of frequency in time and frequency, and so I have these characterizations. And then the long chirp corresponds to this signature, which this is the f to the minus 7/6 in amplitude, and this is cut off simply because it started at a frequency of 10 on this scale. If you ask what the composite FFT is of all these signals superimposed in the way that the image corresponds to, you get this picture here, and at least at the signal to noise I used, you can clearly see the pulsars and the bursts, but this chirp lies completely down in the mud. In no frequency band is there enough power in this signal to pull it out of the white noise background if you simply did a long-term FFT. And yet the integrated signal in that weak chirp does come out to something like order 30. So it would be a detectable signal even though you would not see it if you simply looked at power spectrum. The other thing of interest is asking what does the Fourier transform at high resolution over all the data look like compared to stacking all the power spectra from each of the different slices that I had in the image. And so for that case, what I was looking at was this is the signature, this is the signal of the pulsar. And you clearly have a case where this stands out very strongly above the noise in the high resolution system, but you have a lot more noise in that bin at low frequencies. And you can understand that the difference in signal to noise is something like 30 to 1.4. And that can be understood simply as the fact that in the short-term Fourier transform, these bins are wider, so that the background power associated with the white noise has a contribution that increases with the bandwidth. So the signal to noise degradation goes as 1 over the square root of the bandwidth, and this is roughly a factor of 30, which is the ratio between the durations of those two FFTs that I was using in the analysis. However, this is potentially attractive for for a certain class of problems where you want to look at many different ways of projecting the signature using different modulations of the Earth motion for the pulsar. And the reason one might want to consider doing a lower SNR stacking rather than the full-blown SNR, the full SNR high-resolution spectrum is that the computational cost of this is substantially less than that due to the n log n behavior of the FFT. If I do m FFTs, each of which is length n over m, the factor in front drops out, but the log of n over m then is compared to the log of n. And so the improvement factor, if I talk about the cost for m FFTs over one long FFT, has this behavior. And if I had 1 million points in this, and I considered doing, if I had 1 billion points in this FFT, and I considered doing 1,000,000 1,000 point FFTs, for example, the cost would be about a factor of 3 less. So if I consider the image that I showed you earlier, we have bursts as represented as short duration broadband events. Chirps explore the greatest time frequency area and are going to be expected to be associated with black hole ring downs at the end of at the terminus of their frequency chirp. The CW sources have frequency modulation characteristics that depend on the point in the sky and the source parameters, but are essentially CW signals. The stochastic background looks very much like the stationary and broadband white noise that I showed earlier, except that it would be correlated among multiple detectors. And for deterministic sources, the optimal signal-to-noise ratio would be obtained by integrating your signal along its trajectory in the frequency-time domain. If you had a very high energy, high signal-to-noise signal, one could imagine simply taking the signal squared and integrating along that trajectory, which is basically what a square law or power detector would do for you. At very low signal-to-noise in the regime where we expect to be operating, If you have an idea of what the signal might have in terms of its family of parameters would represent a real signal, you can do much better by doing matched filtering, where you multiply a template times the signal rather than looking at the signal squared. If you have no template but you have two detectors, then in some way you could consider the second detector to be a template for you. So you can look at cross-correlation, and in fact that's what is done for the stochastic background. In every case, the optimal the kernel that's done for the integral has a numerator that corresponds to a signal, and the denominator is weighted inversely by the noise power so that you look where the detector is most quiet. The compact binary, the pulsars, and the cosmological signals are representative of modeled sources because you can conceive of templates or representations of signatures that you want to look in the data with. And then transients or bursts correspond to unmodeled sources for which you have different types of time frequency signals analyses that you would want to do on the data. For a given type of source, the optimal filter could be derived by a suitable model of the noise properties of the instrument, considering its noise properties, and then a suitable model for how the detector that you have would interact with a putative signal of that type. And you need to have models of the waveform or statistics or time frequency domain representation of the signal for such an analysis. The more information, the more robust the filter, but any information is better than can be used to make an improved statement about confidence in the end. The best studied sources are the inspirals, and we have many different analyses that provide us with phase and amplitude evolution for the signature, and we can cast these up as a parameterized family of templates against which we want to match the data. The stochastic background, you assume that the gravitational wave signal, at least over the few decades that we will observe, is Gaussian, isotropic, and white, and consequently you can come up with an optimal estimate of the cross-correlation that you would expect between a pair of detectors. And similarly, we would want to look at how a narrowband bar detector would correlate with an interferometer. For the spinning neutron stars, pulsars, these are very long-lived signals. They're not transients. And the daily and yearly modulations due to the Earth's motion can be used to exploit the signature. And the problem is that the frequency modulation for sufficiently long observation time quickly swamps the resolution of the analysis, which means that you have to look. The equivalent of templates here is that every point in the sky has a different analysis that needs to be done with it to coherently demodulate the signal for the motion that corresponds to that observation direction. And by simply looking at the Doppler formula and asking for the differential in frequency shift to be comparable to what you would get if you had a coherent FFT of length t observation, and asking then what patch in the sky can I look at coherently for a period of observation, t observation, the scaling factor you get is that you would have to, for a month's observation time at a 500 hertz signal, you have to decompose the sky into 10 to the 11th pixels. And so you quickly get to a very computationally intensive problem for something as simple as looking for a line that have the right modulations that are consistent with a static position in the sky. For transient phenomena, we have waveforms that are less well known, but we can model them in terms of the volume that they occupy in frequency time. If you recall the burst that I showed, either very narrow, very short time, large frequency excursions, or other shapes or combinations of phase space. And in many ways, these are most challenging because we expect the instrument that manifests its non-perfect behavior most manifestly in terms of glitches and transients in the instrument, as opposed to long chirps. On the other hand, this analysis is most like how the cryogenic bar detector data analysis has proceeded in the past, so we can expect to adopt and adapt experiences and techniques from this community for the burst analysis for LIGO. We want to rely on coincidences among multiple detectors, and there's anticipation that at some point, if we can validate our data to the point where we can make confidence statements, certainly for the supernovae and other types of measurable astroparticle physics observations, we want to look at whether there are coincidences between neutrinos or gamma rays in our data in a statistical sense, not on an event-by-event basis. Events that have waveforms that are parametrizable then lend themselves to an optimal filtering analysis that gives us what the optimal filter is for the analysis under the assumption that the data are stationary. And you start off by postulating that your signal contains a signal plus the noise, where the noise is zero mean and has, has a variance sigma squared. The other reasonable assumption is that the astrophysical signal is not correlated with the instrumental noise. And if you have a family of templates, you postulate that the astrophysical signal then has some normalization times this template, which is a member of a family of I different source templates, which depend on time. If you ask then, if I form a correlation statistic, which is the data convolved with my transfer function or my optimal filter, can I pick Q to make this have the largest signal to noise? And what you do in formulating the problem is you go through and produce the mean of the signal, which then, since we have zero mean noise, corresponds to simply the template convolved with the filter, or in the frequency domain has this representation. Since the noise is zero mean, the deviation in the signal corresponds to the variance of the noise, which can be represented by the expectation value of c squared minus the expectation value of c squared. And you can go through the formulation and come up with the fact that the noise then corresponds to the filtered product of the spectral density of the noise times whatever this filter Q, which is still unknown, is. If you want to maximize the signal to noise, then you want to maximize the ratio of the average of C over the square root of the noise variance, which is equivalent to the same as maximizing the square of the signal to noise, so you can get not deal with square roots in the denominator. If you ask then for a minimal variance of signal to noise squared for the optimal filter, you end up with an equation that says that the deviation in the correlation statistics times the noise squared has to equal the expectation value of the signal times the deviation of the noise, where these deviations are with respect to the filter that's currently unknown. But if you go through and then ask what these quantities are, you end up with variational integrals for the unknown filter delta Q, and that can be represented by these four quantities. And in the end, setting these two expressions equal to each other, you end up with a quantity that's just a C number. This is an integral over all frequencies, so this is whatever its value, it's a number. But you have a frequency-dependent function has to, at all frequencies, equal this other frequency-dependent function, from which you deduce that the filter itself is the template weighted by the power spectrum of the noise times the offset for each of the frequencies at which this template could have occurred in your data series. And indeed, if you put this filter into this equation, you do conclude that these two expressions are equal, and that that's the optimal filter for the analysis. The interesting thing is that by integrating over the signal, you can actually make a statement about detection well before you can perceive that the signal is present from any other, from a pattern recognition perspective. So I produced a chirp checkerboard here just to give us a toy example that is visually appealing. And I added to this chirp checkerboard at different levels of signal to noise per pixel, just a white hash background. And your eye starts to see that there's a pattern somewhere around signal to noise of 4 per pixel. Yet, if you go through and formally ask, knowing this is your template, what the signal to noise is over the entire pattern, you get this integrated signal to noise over the pattern, which I produce simply by taking a product of the data times the template over the, and this is formally the expression that I showed earlier for signal to noise. And what you find out is that you get a respectable signal to noise of 10 even when you only have a signal to noise of 1 or a few per pixel. So even at this point, a template would be able to pull the signal out of that white noise. But then the question, of course, is, what if you don't know where the pattern is located? Okay? Since you don't really have that a priori. What you want to do then is consider how two adjacent representations of the same template that are offset with respect to each other by delta I and delta J in the coordinates might give you an overlap function. Okay, so this is like an ambiguity function that we deal with in chirps. And what you find is that although you get unity response when you get it right, this function very quickly goes down into the mud, so that if you don't know where your signal is located, you have to rely on making many, many tests with different representations of this template shifted throughout the space. And since this function drops off within one unit offset, you conclude that even in this toy problem, if I didn't tell you how the pattern was oriented, you'd need 1,000 templates to go look for the pattern. Well, you can do the same thing with physical chirps, and I'll get to that in a second. But basically then, if I put in the optimal filter that I calculated times the data, I come up with a time series because I inverse Fourier transform back into the time domain, which is a correlation function as a function of time, where for every point in the time series, I'm asking the question, is the signal to noise at that epoch of time greater than the statistical average that I would get if this was simply noise? And this time series is parametrized by the parameters of P, so I go from one time series on this side to many thousands of time series on that side, and so you get a multiplication of the space into which you have to consider the problem. And if you take a post-Newtonian chirp, a simple first-order chirp, and do this overlap integral between chirps with slightly different masses, and ask what the ratio is, this overlap function is, normalized to the perfect match, you get this type of behavior. So you get basically a delta function. And what that means is that if you don't know the value of the mass or the parameters that you're looking for astrophysically, you have to carefully test for many, many possible values of that parameter that are very closely spaced. In this particular case, if I offset by something like 10 to the minus 4, I go from a peak value to something like 60%, which in a volumetric sense would cause you to lose something like 80% of the signals that might have been there if you had been able to properly detect them with the correct value of the parameters. I basically mentioned what I say here. Oh, and from this width, and knowing that you're looking for something around unit to a few units solar mass, you conclude that you need of order 20,000 templates, which is the number that I used earlier in terms of scaling the computational cost. You can do a much more elaborate and correct job of the analysis, and this was explored first, I think, by Ben Owen, and then Satya Prakash, and then Ben Owen, in a series of often quoted references in which they formulate the problem of how you tessellate the parameter space that corresponds to the area of interest in the search parameter space for the n-spirals in terms of a metric that formally can be cast as a g mu nu on the space of the parameters, so that you can use all the formalisms of basically differential geometry to come up with how you want to optimize the template spacing. And the analysis actually, instead of taking place in the M1, M2 mass plane, is transformed to equivalent time domain parameters that correspond to corrections on the chirp time that you would calculate from a simple Newtonian calculation. And these two time parameters then give you a very narrow patch of space into which this triangle maps. But in this space, the templates are approximately equally spaced. So in a typical analysis that we would do, we get data from our data stream. We have to do the pre-processing I mentioned earlier. We have to worry about windowing effects that I didn't mention here at all, but you have to worry about the fact that if you have a finite amount of data, the FFTs assume the data are cyclic, and you don't want to get spurious correlations from the endpoints of your data stream. and you FFT the segment to bring it into the frequency domain. Since I have a template optimization that depends on the noise floor, another thing that one wants to do is ask whether the noise floor has changed for this epoch of data, and you might want to then take into account how to improve or iterate on the optimal filter for this epoch of data. You then compute the kernel, and you multiply it by the Pth template to look for the Pth signal-to-noise value, and you do the inverse FFT to bring it back into the time domain. And then essentially what you do is you look for excess signal to noise as a function of this parameter Tc, and wherever it exceeds a suitable threshold, you claim you have a candidate event, which then you want to record in the database for subsequent analysis down the road. And you iterate on this until you have finished either all the templates or all the data. And in such an analysis, it's possible to come up using the formalism that I mentioned earlier of how you lay out templates by Owen and Satya Prakash, how much computational power is needed as a function of how light a system you want to search for in mass. And what this shows is that if you look for unit solar mass systems at highest data resolution, which is about 4,000 samples per second, we need of order 80 or so gigaflops, which is a rather large and respectable number, actually. But for us, because we're signal-to-noise limited at highest frequencies due to the shot noise of the interferometer, the first thing we intend to do is resample the data to about 1 kilohertz for the initial search, which then brings us down to a few tens of gigaflops, which is pretty much in line with the analysis that I showed you earlier in terms of back-of-the-envelope numbers. If you put it all together in a more accurate calculation that Kent did in our group, then you basically have this behavior as a function of the minimal mass in the binary, that rather than being a straight line, if you worry about the details of how the computation is done and the fact that you have to always do 2 to the n length FFTs, you actually get some structure here, but basically the same trend occurs, that if you're going down to something like unit solar mass for suitably decimated data, we're on the order of a few tens of gigaflops that are required to do the analysis.
Can you just tell us what's on those axes, since it's hard to read?
I'm sorry, this is... these are gigaflops. Sorry, I apologize. I hadn't noticed that there are 2 lines here. It says operations per second. This is 1 gigaflop, 10 gigaflop, 100 gigaflop.
Okay, and on the bottom...
It's the minimal mass in the binary.
That's 3 at the center, is that right?
Oh, that's 1?
Oh, that's 1, okay.
Yeah, 1, 2, 3, 4, so on. I apologize. I will clean this up before I give you the PowerPoint. So the next question is, how well can we keep up with the calculations? These curves that I show here are theoretical. These are the first hints of performance coming from our engineering run, and these data were compiled by one of the graduate students from the Milwaukee group. And what you find is that what this shows is, since we have the large cluster, you can say, I'm going to do the analysis on 1 node, 2 nodes, 4 nodes, do the same analysis repeatedly during this test on a progressively larger number of nodes, and then you ask, how does the total computational time end-to-end decrease as a function of the number of nodes you use? And if you had a pure scaling, this would be a 1 over n law, which is this the red points I show here. And on a log scale, you see that you start to deviate so that the computation, for more nodes, the computation takes longer than you would naively calculate. A different way of looking, of representing the same data is what's called the speed up for n nodes. And so this would be a y equals x line. If I have n nodes, I should get n times the speed up relative to 1 node. And in this performance trend for the actual data, you see that you roll off to some saturation value that is already a factor of 2 below the ideal when you get to 64 nodes. And if you put this together with a simple computing model, and this was first formulated many years ago by Amdahl, you basically say that you have a serial component to the calculation that you can't avoid. Sending data to all the nodes is a serial process. But then you have a parallel part that you can improve on by introducing greater and greater number of nodes. Then what happens is that the ratio between the time it takes for the calculation on 1 node to n nodes, the serial part is unaffected and the parallel part progressively goes to 0. and you come up with an expression of this that can be reformulated. And it turns out that such a simple expression very nicely fits the data that were observed at Milwaukee. And the surprising thing is that it's sufficient to only have 1.5% of the computation be non-parallel or non-parallelizable to produce a factor of 2 degradation already at 64 nodes. The message there is that if we have a 300-node cluster, we would not simply give the analysis to all of those nodes. We would have to a priori partition it into 5 64-node computations so that each of them can realize the curve, or 10 32-node computations to get even closer to the ideal. So these kinds of metrics are important to give us an insight on how the architecture of the analysis is going to proceed. I'm running out of time. For any analysis in which you want to make a statement, you have to know how well all this machinery that you've put together in terms of data analysis algorithms and filtering of data work. So the method that indicates itself is Monte Carlo techniques, where you take the same data that you're looking at astrophysically and you inject large numbers of inspirals corresponding to different distances and different mass pairs, and then ask how well your algorithm sieves those back out to get an efficiency estimate for how many you would have seen given how many you know you put in. You can also get metrics such as what's shown here, which is the distance that you inject the chirp versus the distance that you deduce the chirp. And you want to make sure that you have no biases, that you get the distance statistically on the average correctly. And this gives you a nice idea on how signal-to-noise degradation with signal amplitude degrades your estimate of the noise, of this particular parameter, which would be distance in that case. The 1994 prototype data that were published in PRL and for which there's a GRQC 99, year 99 reference, were over a short period of time, and rather than asking whether the events that may have been seen were astrophysical, the converse was asked about what is the greatest upper limit, the least upper limit that's consistent with the loudest signal that I saw, if I assume the loudest signal I saw is not astrophysical in nature. And by doing a suitable analysis of the efficiency of the system, of the data analysis system, one concluded that for that particular analysis, with 90% confidence, the rate was something within our galaxy of less than a half per hour, which is nothing earth-stounding, since the real number here is expected to be order of 10 to the minus 6 to 10 minus 7 per galaxy per year. But with the efficiency factor, what that gives you an insight is how well ideally one could have done if you had a 100% efficient detector, and even then the rate was only 0.16, and this is essentially limited by the duration of the data. If you look for 24 hours, this number is not going to be any smaller than of order 1 over 24, and this was something like a 24-hour observation, 40-hour observation. The stochastic background allows one to formulate a similar time-dependent correlation statistic where instead of a template, you now say, I want to correlate the data from 2 different detectors and ask what the optimal filter is. And in order for us to correlate 2 interferometers or 2 detectors, they must have overlapping frequency regimes, otherwise you don't look at the same spectral content of the gravitational wave signal. They have to be sensitive to the same polarization state, because otherwise they would not be communicating detectors. And to get a suitable frequency domain overlap, you have to have the condition that the gravitational wave is, which is longer than the baseline of interest, which for LIGO being 3,000 kilometers gives us a very low frequency content, which would be of order 50 or 60 hertz. If you go through the optimal filtering arithmetic that I did earlier for the chirp, you come up with a similar, a corresponding calculation for what the signal to noise should look like for the case of a stochastic background. And there, what you find is that you have to weight the 2 spectra, the correlation statistic that you get. The optimal filter corresponds to the 1 over the product of the 2 spectral densities of the 2 instruments, since you're looking at data from 2 detectors. And I have here a body of references that go through in great detail in describing how that is derived. I'm running out of time, so I'm not going to spend too much time on here, but basically one can go through the same exact type of formulation where you do the statistical averaging of various moments of the distributions, and then ask for when the deviation of the signal goes to 0, and you come up then with what the optimal filter for the analysis is. And it involves a geometric factor that has to do with how the antennae are separated in space and oriented relative to each other, a model for what you think the astrophysical content of the stochastic background is, and then the empirical estimates of the detector noise that appear as the suitable denominator of the optimal filter. I show here briefly data from January where we did a cross-correlation between Livingston and Hanford. And much to our pleasant surprise, in spite of the relative feature-full spectra that you saw earlier in the spectral density, certainly on the correlation time basis of a few tens of minutes, you get a rather surprisingly white spectrum, which gives us confidence that we will be able to progressively reduce the noise floor as we integrate longer and longer with time in this detector there. From such an analysis, then one looks at, as a function of how long you integrate the data for the correlation statistic, you expect to be able to produce a progressively diminishing as 1 over the square root of t upper limit on what the stochastic background signal would be in white data of the type that I showed earlier. I have about another 10 slides.
Fine.
Is that okay?
Go ahead. If people need to leave,
Yeah.
go ahead and leave.
Okay. So the question is that I wanted to finish up with then is how one does burst detection for which you don't have sampled sources. And there one goes back to the question of what it is one is trying to answer, which is that either the data are representative of noise alone or the data are representative of noise with a putative signal. And one worries about two kinds of error that one can make in making a confidence statement of this type. One is the probability that there is nothing there, that you think there's something there given there is nothing there. And the other is the probability that you make a claim there's nothing there given that there was something there. And one is called false alarm and one is called false dismissal. If you have a data series, if you discretely measure this as we do with digitized data, then for any epoch of time you end up with a vector of numbers of length n where each of these are real numbers. And you have a noise time series and a data time series, and you can imagine a signal vector time series that you can model as we've done earlier. And you can ask the question of what the statistical expectation is of the correlation of the noise at different points in time in the series, and this corresponds to a correlation matrix, which is diagonal if the noise is white, because every point is independent of other points, and each one represents the same distribution function. If you ask what the probability of observing a given value for n is, if it's Gaussian white noise, then you get the Gaussian distribution that I showed earlier. But the interesting thing is, if you say, what's the probability that I get the sequence of numbers n1, n2, dot, dot, dot to n, since each one is statistically independent, the probability of getting the vector n is related then to the correlation matrix, and you get a quadratic form of the vector n dotted into the correlation matrix, which in the limiting case of one dimension gives you the simple Gaussian. So if you have a signal if you have a data series X that has no signal in it, then you expect that the distribution of X will mimic the distribution of n and can be represented in this fashion. If you have data with a signal, then subtracting the signal from the data will give you a distribution that once again mimics the noise. So you have an offset of the data by the signal with the same distribution that you got earlier for the noise function. In order to come up with an assessment of how likely it is that you see an event or not, you need to go through and understand how you can make different probabilistic statements on what you see versus what you expect. And everything begins with the formulation of Bayes' law for the problem, which is that you measure a signal x, and you can calculate the probability that that x is consistent with the data, or with a model S sub I for your data. But what you really need to answer is what is the probability of that model given the data. And by using the Bayes' law formalism, it is possible then to re-express the probability that the data correspond to this model as a probability that this model corresponds to the data times the probability that the model is correct, and then the probability that the data contain no signal, and then the probability that the data contains some signal, which comes from expanding the probability of the data is the probability of the data with no signal plus the probability of the data with any signal. The likelihood ratio, big lambda, Greek lambda, then is defined as the ratio of probabilities, is proportional to the ratio of probabilities of the data given a signal versus the data given no signal. And by using the covariant expressions I showed earlier for Gaussian noise, and remembering that you can express this as x minus s for 0, it turns out that quite nicely you get a linear behavior on x, an exponential of a linear function of x, which represents the probability ratio between the signal being present in the data and no signal being present in the data. What this means is that if you do a histogram on, let's say, the time series for the correlation function that I showed earlier that comes out of the analysis, for any data set, you would expect that you get some distribution of answers for the correlation, which, if there are no signal, would be distributed with 0 mean. And for a signal present of strength mu, you would expect the Gaussian to be offset by the mean of the signal. And so the question is asking what the likelihood ratio is the value of the distribution function on the blue curve taken to the red curve. And what you can see is that if you go to higher and higher thresholds, asking progressively for stronger and stronger signals in your data, the tail of the false alarm quickly goes to 0, and you sustain for some period of time a sufficient probability for detection, but eventually if you make your threshold sufficiently high, both functions go to 0. So the art of any analysis is to pick your threshold as a function of the observed data in a manner that gives you the most restrictive statement that you can make about the data, the astrophysical observation that you want to quote. If you go and ask how you might look for bursts when you don't have a parametrizable set of templates, then there are two methods that come into play depending on whether you have a prior knowledge of P or whether of the template space, and whether you want to maximize the average likelihood that you make a detection, or you want to make sure in a conservative sense that you never make a false dismissal given that you have a certain false alarm rate. Time is short. I'm going to focus on the excess power statistic here. The idea here is going back to the frequency time map that I showed earlier. One asks for a little patch of frequency time space, how much power is distributed there, and can I make a statement about how that power is distributed? And if I exceed a threshold, as I showed in the previous few slides, then what can I say about the probability that there's an event here? And by formulating this problem in this measure, normalized to the average noise throughout the plane, we have a power statistic that then can be used as a trigger on whether or not you see an event. The question that comes to mind, though, and I purposely inserted something here that had a structural feature, what if the feature is not rectangular? Well, the trick then is you don't want to fix the shape, but possibly look for clusters of neighboring pixels that exceed some statistic and identify the cluster as an event rather than a priori asking for events that fill a rectangular region. And this type of analysis is known as time-frequency cluster analysis, and is the current thesis project of Julian Sylvester at MIT. There are a couple of presentations he's made at various conferences on the subject. He has a very elegant paper in process that will outline in a definitive manner the analysis techniques that would go into such formulation. The strategy then applies where you only know something about how long signals have duration over and what frequency regime they might occupy. If you knew more about that, you probably would be better off using a template-based search if you can make a better statement than just a time-frequency window. And it's important to divide by the power spectral density, because otherwise you're implicitly assuming that all signals are equally likely, but that's not the case, because in certain regimes the noise spectrum may be changing, and so it's not as likely to detect a signal as it is in a regime where the signal to noise is sufficiently low. The idea is you pick a start time and you pick a frequency window, you do the FFT as we've talked about in the past, you sum the power, you calculate the probability that what you see there is simply a chi-square distribution distributed with the appropriate degrees of freedom of the number of pixels you've chosen. And if your probability is significantly small, that it's noise alone, you record this as a putative detection for follow-up. And you simply walk through your frequency time map to look at this for all possible choices of start times and frequency windows of interest. If I have multiple detectors, and I'll be finishing up, then we can actually use data independently collected at multiple sites to combine into a proportionally better metric for how one, with greater confidence that a detection has been made. I just wanted to remind people we have two observatories separated by 10 milliseconds in light time travel, and they were originally surveyed so that they are optimally aligned for the same polarization sensitivity, in the sense that one of the two arms lie on the same great circle that connects those two observatories. In addition, over the same decade that we've been building, the Europeans have two different endeavors. One is the Virgo project in Italy and France, and the GEO project in the UK and Germany. And the Japanese have been building a 300-meter class interferometer in Japan that we want to eventually use as a coherent network of detectors looking at the same instant in time, potentially for the same putative sources. I should mention that there is hope that eventually in Australia a southern observatory might be built, which would give us better coverage than the skewed distribution of detectors that we currently have, which are all dominated, are all in the northern hemisphere. If you have multiple detectors and you ask for a coincidence window, first of all, the window is very narrow, even considered on a worldwide scale, so that we would have at most something like a 90 millisecond coincidence requirement, even for data collected at very high bandwidth. And then if you ask what the effective coincidence rate is, if you have n detectors, each of which has a one-sided event rate of lambda, then if you have n comparable detectors, what you find is that the effective data rate for n coincidences normalized to 1 is a power of a small number that's equal to the n-1 sites that you're observing from. And this is the event rate, and this is the observation window, which in our case was of order 80 milliseconds. To give an example, if you have a 1 per minute glitch rate in any one interferometer, and we have 3, then in a 20 millisecond window such as we have for LIGO, you reduce the once per minute by a factor of 10 to the 7th. And if you have the inclusion of Virgo, for example, then a once per minute glitch rate in each of the detectors is reduced to a minuscule few parts in 10 to the 10th, which immediately produces a much greater confidence that if you've seen something in multiple detectors, that you can have credibility that it's not produced by a transient phenomenon in any one detector. If you take this equation and then ask the following: if I want to stay below 1 event per decade of false alarm rate, and I have one detector what can I have or tolerate as the individual detector rates, such that I can meet this requirement that if I do a coincidence analysis, I have a better than the target goal. Then by the time I use all the LIGO interferometers, I can get to a once per decade false alarm rate with something like 50 to 70 events per hour in one detector, or once a minute number. And if I can bring in Virgo and subsequently Geo, I very quickly get to the point where I become very forgiving in the individual performances of the detectors by requiring a coincidence. If I consider the globe, I have this solid polyhedron that's formed by the vertices of the detector. And for each one of those, then I have a baseline. And relative to the baseline, then I can ask the question of how well I can detect the source in the sky. And if I look at the geometry and say that I have an uncertainty delta t in the sample in the time of occurrence with a baseline d, then for the LIGO detectors where d is of order 3,000 kilometers, if I naively put in the sample rate of the detectors, I get something like a half a degree resolution. In principle, I can define the event much better than the sample rate if I have sufficient statistics, but that sets the order of magnitude of the resolution with which a pair of detectors can operate. So if I have this cluster and I have a source at a particular point in space, every pair of detectors gives me a putative position for the source, which is this cone relative to the baseline. As I add detectors, the great circles, or the circles, the cones that are swept out in azimuth in the sky progressively get better and better localization, because the detection, it has to be consistent with what's observed by all the different baselines. So in closing, if I have a putative detection in multiple detectors, what we would first do is ask for a coincidence in window that says it's a consistent point in the sky and it's consistent with the detector observation resolution. It has the correct amplitude of the signal, and the astrophysical parameters are all consistent among the detectors. But ultimately what we plan to do is to do an independent follow-up analysis, where instead of dealing with n individual detectors, we deal with one superdetector for which we have a vector of strains h. The log likelihood function that then is maximized for the detection becomes a vector over the parameters and a vector over the strain. And the noise functions that I represented in the denominator of the optimal filters then become the cross-spectral densities of the noise between pairs of interferometers. And the same signal-to-noise function that I had before now is the vector H transpose dotted into the covariance matrix times a vector of templates, where you require that this family of templates all come from the same fundamental set of parameters, and it's a projection of how each detector sees the same fundamental astrophysical waveform. Sam Finn and Sukante Boza have a couple of papers over the past several years that go into great detail in how such a formulation can be efficiently rendered for a follow-up analysis on short stretches of data. I'm finished.
No, we don't need to change anymore.
No. I apologize for running over.
Yeah, it's an equal tour de force of the entire subject. Should be good to have on the web.
Thank you. Okay?
Good.
Thank you.